Hello friends and welcome to the third lecture of fourth module, Computation of Gradually Varied Flow Profiles. So in the previous two lectures we have seen what is a gradually varied flow profile, what is governing equation of GVF profile, what are the types of water surface profiles, that is a drawdown profile, backwater profile. Then we saw their analysis for different slopes, and today we will try to compute the length of the GVF profile. So our learning objectives to understand the significance of Froude number in GVF computations, to establish control sections while we analyze GVF profiles, and finally we compute the length of GVF profiles for both prismatic and non-prismatic channels. So let us understand what is the significance of Froude number. So Froude number in a turn will give us an indication how the flow is behaving, so that we have already seen while we are discussing the critical flow. So little bit elaborated discussion is presented here. So the gradually varied flow is usually a differential equation, and we need some boundary conditions to solve that differential equation. Now from where these boundary conditions would arise? Mathematically, if we see that the flow depth at any section is a boundary condition because you have dy by dx, so y at different sections can serve as a boundary condition. But in order to correctly represent the open channel flow boundary, either we need an upstream or a downstream boundary condition, and that too depends upon whether your flow is supercritical or flow is subcritical. So let us have an experiment. So we throw a pebble in still water. So what will happen if we throw a pebble in still water? You can see that it will create some disturbances which are in the form of concentric circles, and it propagate outwards. So from the center, it will propagate outwards. So that form of disturbances can be seen. Now the speed with which the disturbances propagate is called celerity, or celerity of gravity waves in shallow water. So it is evaluated as C is equal to under root GD, where D is the hydraulic depth. Now, what will happen if the same pebble is thrown in a moving water which is having a velocity V? Now the wave propagation will no longer be in form of concentric circles because the water has some velocity. So the Froude number can be expressed as F is equal to V upon under root GD, but under root GD is nothing but C. So F is equal to V upon C. So Froude number is a ratio of the velocity of flow to the celerity of flow, that we have discussed earlier also. Okay, so let us understand here. In case of still water, the velocity is zero, so it propagates in concentric circles in both the directions equally. Now we may have different types of flow, so let us begin with the subcritical flow. So in subcritical flow, your Froude number is less than 1, and thus your velocity is less than the celerity of the wave. So in this case, your disturbance travel upstream at a speed of v minus c and downstream at the speed of v plus c. So both upstream and downstream movement is there with respect to the a point where the disturbance is created. So this is the point where the initial disturbance is created. Now if we go for the critical flow, you know that the Froude number is 1, so v is equal to c. So in that case, the upstream edge remains stationary, that front is not moving, while downstream it is propagated with a velocity or with a speed of 2c, that is twice the celerity. And in case of supercritical flow, your Froude number is greater than 1, and thus your velocity is greater than the celerity. So the propagation is only in the downstream direction. So you get the propagation in the downstream direction only, such that the back end will have a velocity speed of v minus c, and the front end will have a velocity of v plus c. So only the downstream propagation is possible, and there is no upstream propagation at all. So this is what the flow conditions depend, and thus based on this flow condition, so the disturbances propagate upstream in case of a subcritical flow. So the conditions at downstream of the channel would affect the flow. So this implies that the supercritical flow is subjected to a downstream control. So there is a downstream control for a subcritical flow. Correction, subcritical flow. So therefore, whenever you are trying to solve a GVF equation for subcritical flow profiles, now you know which are subcritical flow profiles. Like M1 is a subcritical profile, M2 is a subcritical profile, S1. So there, the downstream boundary condition is needed because there is a downstream control. In case of supercritical flow, your flow cannot propagate upstream. So the supercritical flow in a channel is not affected by the downstream conditions as long as the flow remains supercritical. So therefore, flow is subjected to an upstream control, and when we are analyzing the flow profiles which are in supercritical zone, so that time we will take the upstream boundary condition. So like your M3 profile, your S3 profile, S2 profile, so these will be having an upstream boundary condition. So with that basic understanding, we move ahead and we see that how the control sections are identified when we are analyzing the GVF profiles. So just to recall, a control section is one where we have a definite relationship between depth and discharge. So your weirs, spillway, sluice gate, etc. are some of the examples of the control sections. Now, why a definite relationship exists? Because the depth is critical depth. So you, for a given specific energy, you have only one depth. So that is why a critical depth is also a control point. So anywhere in the channel, if you are able to achieve the critical depth, then it is also a control point. However, it is effective in flow profile which changes from subcritical to supercritical. So the critical point will come in both the cases, when it is from subcritical to supercritical and supercritical to subcritical. But in the reverse case, where it is from supercritical to subcritical, we have a hydraulic jump. So that hydraulic jump passes the critical depth. So that is why the control point as a critical depth in hydraulic jump is not much efficient, but in the other case around, it is very efficient. Now, it is very important that any GVF profile will have at least one control section. It can be more than one also, but there will be at least one control section. So what are the types of control? So there are three types. One is upstream control, one is downstream, and third is artificial control section. So let us understand the upstream control section. So when it occurs, when there is a steep reach at the upstream end, because the flow in that channel has to pass to the critical section at the upstream end and then follow either S1 or S2 profile. So you can see that this is a steep slope channel. So the flow is initially here, so it has to come down. So while coming down and meeting the NDL, it has to cross the critical depth. So this is your YC. So that particular point becomes the control section. Similarly, in case of S1 profile, after the jump is formed and it meets the what I can say, the pool level, which is due to the sluice gate. So so this is your control. So this section becomes a particular control in that case. Now, if the downstream water surface is very high, it may raise the flow surface at the upstream control. Also, so in this case, you can see that the downstream water surface, when we compare to this case, this water surface is very high because of the sluice gate, there is ponding. So that case is represented here. Also, when there are several steep reaches, so let us say one slope followed by another and so on. So the control section is at the upstream of the uppermost reach. So if it is a composite profile, so on the uppermost reach, there will be a control section. The upstream control also occur when there is a long mild reach channel. because your curves m1 and m2 will ultimately approach the normal depth. So that case also you can have a upstream control. So it is not only in the steep slope, but for a mild slope also there can be an upstream control. So here, if you can see, this is an m2 profile. So in this case also there is an upstream control because it is a very long channel, and ultimately the depth will be approaching the normal depth at the upstream end. Okay. Now the next is a downstream control. So when this downstream control occurs, so this downstream control occurs in any long steep reach or steep slope channel because the flow will approach the normal depth at the downstream end. So in a steep channel, ultimately the flow has to approach the normal depth. So if the downstream end of a mild channel terminates at a free overfall, then the control section may be assumed at the brink where the depth is critical. So here, if you can see this M2 profile, so there is a drop in the channel. So at this particular point, this depth YC, so this is called the brink depth. And here your control section is there. Similarly, in horizontal bed channel, at the brink, your depth is YC and this is your control section. So this is the downstream control. If we look uh, here, so in this case also this is an S2 profile. So S2 profile has an upstream control. Then we have an M2 profile, so it has a downstream control. And what is an artificial control? Artificial control is obtained by inducing a structure such as sluice gate, dam or weir, and that is an artificial control. So here we can see all three types of control sections. So now we move on to the gradually varied flow computations. So usually the GVF flow profile computations, they involve the solution of the dynamic equation of GVF or the differential equation. Now there are three main methods which are used for this. The first is the direct integration method. Now this method is very complex, so it is very less adopted. Second is a numerical or step method. This is most widely used method. And third is a graphical method. Although it is accurate but is a bit tedious, and thus it is practically obsolete. So let us discuss the first method, that is a direct step method. Now the direct step method, in which a step or in general a step method is where you divide the entire channel into small reaches and you carry the computation for each step. So step by step the computations will progress. So that is a step method. That's where the name is derived. So this method is simple, very simple, and it is only applicable to the prismatic channel. Remember, direct step is only applicable to prismatic channels. So let us consider the differential equation of GVF. So we have dE by dx is equal to S naught by SF. So we are writing this in finite difference form. So it becomes delta E by delta X, that is S naught minus SF bar, where SF bar is the average friction slope in a given reach delta X. So rewriting this equation, we have delta X is equal to delta E upon S naught minus SF bar. So if you have two sections, so your delta X will be X2 minus X1, that is E2 minus E1 upon S naught minus half of SF1 bar plus SF2 bar. So that is the average of the friction slope. Now, this equation is used to calculate the GVF profile. So let us have the steps which are to be followed to analyze or compute the length of GVF profile. So in the direct step method, you can see that you're dividing into different sections. So this is section 1, section 2, and you're then proceeding to n plus 1 sections. Okay. And the distance between two sections is your delta x. So what is the given data? You have the discharge, you have the longitudinal slope, you have the Manning's roughness, and the channel cross section properties is given to you. So first step is you compute the normal and critical depth. Based on that, you can find the slope of the channel, whether it is a mild, steep or critical slope. Then you can identify the GVF profile, that whether that profile is occurring in a subcritical flow or supercritical flow. So let us say you identify the mild slope channel. Mild slope channel, then based on Froude number also you can identify the flow. So you say the flow is, let us say, subcritical. So mild slope and subcritical, there are two combinations in the first zone or the third zone, so M1 or M3. Then you identify the profile based on relative comparison of y, yn, yc. So if your y falls in zone 3, it is an M3 profile, or it forms in zone 1, it is a M1 profile. And based on your subcritical or supercritical condition, you can also analyze the control sections. You can determine which are the control sections. So we'll represent the solution in terms of a tabular manner. So the first thing is area is depth of flow is given to you. Then you compute. Now I'm demonstrating for a rectangular channel. So then you compute the area of flow, that is b into y. Then you have the wetted perimeter b plus 2y. Then you have the hydraulic radius a by p. Now then you need to compute the velocity of flow. So the velocity of flow, that is given by Manning's equation. So you can simply apply the Manning's equation and get the velocity of flow. Then you have the specific energy, that is y plus v square by 2g. Then you have the delta E. Now here I'll explain how to proceed. So let us say you have some values. So I'll just give you some dummy values. So let us say this is 1, this becomes 2, and this becomes 4, this becomes zero point 0.5. Let us say you have an arbitrary velocity 1, this becomes 1 point something, let us say 1 point x. Then the question is where to get E2 by E1. So now you come to section 2. So that is a serial number 1, serial number 2. So these are the number of steps you are doing. So these are the steps. So again, let us say you have this 2, you have 4, then here you will have 6, considering b equal to 2. So this will be like 0.67. Here you may get something as 1.2. Again, I am putting as 1.x1 and so on. So this is your E1 and this is your E2. So here the first column will be blank, and here you will write what is E2 by E2 minus E1. Similarly, here you will calculate SF, that is n square v square upon r is to 4 by 3, and here your SF bar will be blank because SF bar is again average of first and second section. So you have here two values and you get the average SF bar. So here again S naught minus SF is blank. Okay, again delta x is blank and your x is 0. So here you get the SF S naught minus SF bar. So again you have some value, then you get delta x. Let us say your delta x comes out to be 5. So here you will, what you will do, you will do cumulative. So 0 plus 5 is 5. So after all the computations, here it comes out to be 15. So you will add 5 plus 15 is equal to 20. And after, let us say here it comes out to be 60. So 60 plus 20, and that comes out to be 80. So you are doing only 3 steps. Okay, so you are 4 steps. Sorry, you are doing total 4 steps. And whatever the value you get here, this is the length of your GVF profile. So it is 80 meter in a given problem. So that way, how many number of steps, if it is specified, do in 4 steps, do that. If not, at least you should do 2 or 3 steps. The more number of steps, the better you are able to get the result, because otherwise you will approximate the profile to be a straight line if you just take 2 number of steps. So this is how you compute the length of GVF profile using the direct step method. So all the formulas are given here. So the same table you can adopt and very easily you can get the GVF profile length. Now, there are some useful hints while applying this direct step method. The calculations must proceed upstream in case of a subcritical flow and downstream in case of supercritical flow to minimize the errors. Okay, so let us say if you have a dam and you get an M1 profile, so you start from this point and proceed in the upstream direction because it is a subcritical flow. And if it is a supercritical flow, then you take this and then proceed in the downstream direction so that your errors are minimized. Now, it is not necessary that the steps you take has to have equal increment. So if your, let us say your initial depth here is 1 meter, and your final depth is, let us say, 5.5 meter. So it is not necessary go in equal steps. You can go for unequal steps. Let us say first step is 1 meter, then 2 meter, 1.5. You can go that way also. Now, where to terminate your step, that is very important. So the termination criteria is given that your depth will reach 1 plus or minus 0.01 yn. Now, why that criteria is given? Because let us say you have a M1 profile. So this is your NDL. So when you sketch this profile, it is somewhat like this. So never this particular curve will touch NDL. It will be asymptotic to NDL. So that is why that 0.01 is given, so that your curve never touches that NDL. So it terminates at that point when it is 0.01 lesser or more than the yn. So here it will be 1.01 because it is in first zone. If it is in third zone, it will be 0.99 yn. So there you have to terminate. So let us say your yn is 5.51, then you have to terminate at 1.01 of 5.51 in case you are having an M1 profile. So that is very important. So as I told, the accuracy would depend on number of steps, and also you should be very careful while you calculate delta E. Now delta E will be a very small value. It may be in some decimals like 0.1953 and so on. So if you round up 0.1953, you round up to 0.2, then you could incur errors. So there you have to go for at least 4 or 5 decimal digits because the values are very small. Same in case of S naught minus SF bar also, that you have to do very precise calculations. So this is about the direct step method. Now let us move on to the standard step method. Now the standard step method, as we know, the direct step method is only suitable for prismatic channels, which are artificial channels, because there are some difficulties when we apply it to the natural channels or the rivers. So in that case, uh, we have a standard step method which is applicable to both prismatic and non-prismatic channels. In case of non-prismatic channels, the hydraulic elements are no longer independent of distance along the channel. So that is why you need to make some modifications while account for this non-prismatic behavior. So the sequential determination of stage is a solution of the problem. So here you have to sequentially determine the stage, because let us say in a prismatic channel, if you look in the plan, your width and cross section may change. So at every change of section, you have to determine the stage sequentially. So here you get the trial and error based solution of your energy equation. So when we are considering this, let us say there are two sections, section 1 and 2, where your section 1 is in the downstream of section 2 and they are separated by a distance delta x. Okay, now whenever you're calculating using this method, your calculations should proceed in the upstream direction. So that is what here it is. Now the total head loss where we get from this method, that is divided into different components. So this is the head loss due to velocity, there is a friction loss, and there is a eddy loss. So that is how the head loss is categorized. So the energy equation at both the sections, it can be given as Z2 plus Y2 plus alpha 2 V2 square by 2G is equal to Z1 plus Y1 plus alpha 1 square V1 square by 2G plus HF plus HE. HE is the eddy loss, HF is the friction loss. So friction loss is estimated using SF in bar into delta X, where SF bar is half of SF1 plus SF2. So that is how the friction loss is determined. While the eddy loss, it is determined using this equation where HE equal to CE alpha 1 V1 square minus alpha 2 V2 square upon 2G. Now there are two cases. Let us say if you apply this equation for prismatic channel, then your eddy loss will become 0. So that component is eliminated. Now what about gradual and abrupt transition? So let us say your width changes. So you have two sections. So this is your width B1 and this is your width B2. So the change in the width is very gradual, and that is why the coefficient values are less. So this is an expansion, and the opposite of this can be contraction. Now if there is an abrupt transition, so let us say it can be something like this. This is an abrupt. Okay, so this is your B1 and this is your B2. So in this case, the transition is very abrupt and this is a contraction. So based on that, the coefficient has to be applied. So if you denote the stage h equal to z plus y and the total energy h, then using suffix 1 and 2, we can represent the parameters at appropriate section. So the total energy h is h plus, where h is your stage, that is z plus y plus alpha v square by 2g. And if we put this in equation 7, your equation 7 becomes h2 is equal to h1 plus hf plus he. So this is the equation 7. So here, when you're solving using this method, you know H1 and the channel geometry and discharge is given to you, and then you perform some trial and error solutions. So let us see how you will proceed in that case. So you are given, let us say you assume a trial. So you start with a trial value. So you get, this is, let us say this is your first trial. The elevation of bed is given to you. So I've written here, it is given. The depth of flow. So initially you have to assume a depth of flow. So let us say I assume x meter. Don't assume a very big value. Assume which is, let us say 2 meter or 3 meters. So something that value you will assume. Then you will find the stage, that is z plus y. Then area, perimeter, hydraulic radius, velocity, head, v square by 2g, and total head, that is z plus y plus v square by 2g, that is h1 you get. Then you can find the energy slope sf bar. So here there will not be any sf bar. So when you have this calculation, you can take the average of that and represent the sf bar here. Okay. Length is given to you. So whatever the length of the reach that is given to you. Friction loss. Now this everything is not applicable in the very first place. So you just come down to the next section, because there will be different sections will be given to you. So between them only you have to do. So let us say you have a section A, then section B, and then you perform the trials. So friction loss you can calculate using the equation 8, eddy loss using equation 9. Then you have H2, that is your H1 plus HF plus HE, and then you will compute capital HE, which is the difference of H2 minus H1 plus HF plus HE. So that is the difference. Now here the now this H2, you may be confused that why we are doing here this subtraction and this. So now this H2 takes this H1 of the previous time step. So previous step. So let us say you're calculating this H2 here. Here you're not calculating H2. So this H1 is of this step. So from here you are taking H1 and there you're taking HF plus HE. And so that is why this answer will not be, HE will not be 0 initially. Okay. So that is how you compute it. And your delta Y2, that is the correction. Now you have an initially assumed value. Let us say your assumed value is X and you get another value Y. So there's a difference between this X and Y, and that is a correction which is delta Y2. So whatever the assumed value is taken, and to that assumed value, let us say you assume the value 3 and your delta y comes out to be plus 0.3. So next assumed value you will take as 3.3. So that way you will take the next value as 3.3. So you'll go on adding if the correction is positive, if the correction is negative, you go on subtracting. So at a time, the time will come where your HE becomes very close to 0 and your delta y2 is also very close to 0. It can be 0.001 and 0.001. So that means your solution converges and your assumed value and the computed value become same, and thus you reach to a point where your solution converges, and thus the length of profile can be estimated. So this is how your standard step method works. This is a bit complex because it involves lot of trial and error. So that is why unless and otherwise it is required for prismatic channels, you will use direct step method only. Standard step method is very complex and very tedious because it may involve lot of trials. So with this understanding, we complete this lecture, and next time we'll start with module 5, that is the rapidly varied flow. So thank you everyone and have a nice day.